Okay, let's spend a little bit of time just talking about film screen imaging. This will be kind of loosely related to film screen characteristics, because what I want us to do is just to see how film screen actually works before we talk about the characteristics of it. So some of this I think the ART has removed from the board outline to its detriment, because it's difficult to talk about characteristics of this stuff if we don't really understand the chemistry of how it works, right? So this is not a picture of Mars. This is a electron microscope image of film in cross section, and so we can actually see. Do we need to turn the lights down?
Yes.
Lena, do you mind hitting the lights? We can actually see different layers to it, right? So this would be a protective coating out here, and then this is the actual crystals. We can see all these different crystalline structures through there, right? Then there's going to be some kind of adhesive, right? And then a base, a clear base. I think this is the base. I take that back. This may be the adhesive layer right here. I believe this is the base, and then this is another level of protective coating. Okay. But I think that's a really pretty picture. So overview. We're going to talk about film composition, what a base is, what emulsion is, what the different parts of the emulsion are. Then we're going to talk about the characteristics. The characteristics are the part that are continuing to be talked about by the ARRT. But again, in order for us to understand it better, let's talk about composition real quick. Today we're just going to very loosely address sensitometry. This slideshow doesn't have a real in-depth discussion of it. Okay, cross-section of a film. We're going to have, again, a protective coating, some kind of emulsion. That's what actually develops and has an image in it, is that emulsion. Then some kind of glue that's gluing it to a base. And if you notice, the thickness of the film is largely just the base, right? And then this would be a double emulsion film, because it has emulsion on this side as well as emulsion down on the bottom, right? So we'll just file that away in the back of your mind that this is a double emulsion film, and we'll talk a little bit more about how that works later on. So the base. The base is going to be made out of polyester, right? Just like discotheque stuff, like Saturday Night Fever. It's going to be 0.008 inches thick, or thereabout, right? Really, really thin, but thicker than the other stuff. And then typically with X-ray film, they've added a blue dye to the base, and that just helps us see contrast in the image more clearly. So it's going to enhance the contrast, it's going to reduce the glare when we throw it up on the light board. So base is just polyester. The emulsion is what actually does the work of the film, right? And emulsion is primarily silver halide crystals suspended in gelatin. And yes, that is like the gelatin that you buy at the store, right? And so horse hooves and things like that. But it is just a clear fluid that holds these crystals in it, right? Of the silver halide crystals, there's going to be these little silver bromide pieces inside of it that have sensitivity specks on the surface. And we'll talk about what the sensitivity specks are and what they do in a second. And then again, the gelatin. And it's just an easy suspension, and it actually expands and contracts during processing. So the developer is going to allow the gelatin to expand, and then the fixer is going to make it contract and harden. So there is the house that Jello built. Just a way to fix this gelatin thing in our mind. I have no clue what this is referring to, but in Utah, gelatin was like an art and a science. People were very much like if you were having an office party and there was not 4 or 5 Jello molds at the office party, something was wrong. Like someone had died or something. So I don't know. Jello for me has had an interesting history. Does anyone here eat Jello? Kind of. Yeah. All right. I like the Jello molds that look like brains. Okay. So within that gelatin, there's going to be crystals that have little tiny impurities in them, and then we're going to call that a silver sulfide. Okay. And this is what we're talking about when we're talking about sensitivity specs, right? And these are the centers that make or hold the latent image, right? And looking at Callaway, the Mosby guide to the board test, in the 3rd edition, he has this definition on page 57. It says, it's a latent image is the image contained in the silver halide crystals after exposure, but before development, before these silver bromide impurities have been removed. Okay? The silver will actually fall off of the film when we develop this, and all that's going to remain is the speck, right? So back in the day, we had silver recovery systems, where in the developer tank, they had a filter that would fill up with silver. You could take that silver to the bank. You know what I mean? It was actual pieces of silver. Ditto with old school, like all those films that we keep in that bucket in there. At some point, we will probably be able to sell those films. They will do something to those films to remove all the silver from it, and then you could make jewelry out of it or whatever. So the silver is a significant part of how this process works. Has anyone ever seen silver that has not been polished for a long time? What happens to it? Yeah, it turns black, right? That's exactly how this system works. So anywhere that the silver sensitivity spec gets hit by the crystal breaks and the ions that activate that center, it's just going to turn black. It's going to tarnish. So it's going to be a density on our film, right? It's going to record that as a density on our film. So let's look at a little bit of how that works. This is an example from photographic film, but the exact same process is at play with our radiographic film. The difference between the radiographic film and the photographic film is radiographic film is sensitive to both X-rays and light, right? Because we put it inside of an intensifying screen. The film doesn't care if it's light energy that's coming in or if it's an X-ray that strikes the crystal. It's still going to do the same thing, right? But the intensifying screens are part of the process now. It helps us do this that much quicker. So we have an unexposed grain of in the emulsion, and the light strikes it, right? And what happens is it knocks all of, so it's exposed now, and all of the little electrons fly outside of it, right? And they congregate around this speck here. This is the silver bromide. I'm sorry, silver sulfide. I apologize. Now all of these ions are going to be attracted to that sensitivity center, and they're going to darken that sensitivity center. Okay? And then it's going to sit there. It is a latent image, right? It's not until we actually develop it that it will become visible to us. We could look at the picture all day long, we wouldn't be able to see it, but it is there. It's buried in these sensitivity centers. So, emulsion can be a double emulsion film, like what we were looking at earlier in that cross section. We can also call that duplicitized, but most places I've been at, they called it double emulsion. And most films that we see are a double emulsion, I believe, just because they're that much more quick. We'll talk about how speed works, but double emulsion is going to be a faster image. Single emulsion film, and this is going to be coated just on one side. So it's going to be more sensitive, it's going to be slower, right? Because it does not have emulsion on both sides. So it's not as thick of an emulsion layer. So quick review. A double emulsion radiographic film base is composed of what? The base is polyester, right. Yep. Most all film bases are composed of polyester dyed blue to enhance the contrast of the visible image. So, it's the truck going by. Yeah, whenever that thing shakes, it's because big trucks go by on Madison. And the only reason I'm aware of that is because I worked at an MRI center, and whenever big trucks went by the MRI room, it was very close to a road, and if they used engine brakes or anything like that, it would actually cause an imaging artifact on our images. Because the MRI room is a sealed, quiet room. You know what I mean? It needs to be quiet in there for it to pick up the signal. But now that we've kind of talked about, so I gave us a very, very, very loose overview of what these images, how the film is, what it's composed of, right? The significant things there's the silver things, silver halides, the silver sulfide, silver bromide, and then that base of polyester, right? Now that we understand those concepts, or we've at least gotten an overview of them, we can better kind of more readily understand how the characteristics of film work, right? So, number one, let's talk about speed, or we might call it sensitivity. It's going to be determined by the size and number of silver halide crystals and the thickness of the emulsion. So this goes right back to that double emulsion film that we looked at the very beginning. It is thicker because it has emulsion on both sides. Therefore, it's going to be twice as fast, right? Technique and speed are inversely proportional. What does that mean? If I have mass can go down, right? The faster the film it is, the less technique I have to use. Good, thank you. And we'll talk about a formula to determine that. So the larger the crystals and the thicker the emulsion, the faster the film. So large crystals are faster than small crystals. And a double emulsion is twice the speed of a single emulsion. And that comes from Bouchon. Here's a formula that's very, very valuable. When I took the board, this formula was on there twice, I believe. Applications for this formula. I think it's helpful for us just to be aware of it, that it's an inverse proportionality, like we were talking about, and to be aware of just how to do this calculation so that we're not scared of it. Another thing that's very, very important to kind of emphasize at this point is that when we're applying this formula, this is a relative speed, right? And that is, we call it a relative speed because it is both the film and the cassette, right? So the film and the screen are working together to produce a relative speed, right? We have this film is a certain speed and it's receptive to certain colors. The cassette is a certain speed and it produces certain colors. We have to get the right film and the right cassette, otherwise there's no telling what we're going to see, right? So if we're working with a film screen system, say the zombie war actually happens and we're all stuck on an island somewhere and I have a broken toe and I need you to do an x-ray of me, and we discover this x-ray machine. I've gone too far with this crazy story, but we discover an x-ray machine on the island, right? The very first question we should be asking is, does the screen match the speed of the film, right? Or are you going to be frying my foot with x-rays because the screen and the film don't match, right? So if you're ever working at a clinic where they're using film, and some places still do, that is a valid question to be asking. Do you use different speeds, right? Because sometimes at orthopedic clinics they used to have like a fast film for certain kinds of exposures and then a slow film if they needed more contrast. Questions about that? Okay. During the lab, I'll have one group working this formula on a worksheet and another group will be in the lab working on technique charts. So let's talk about contrast. This is going to be determined by the size of the silver halide crystals and the thickness of the emulsion. So clearly it already is related back to speed, right? It's a function of speed. The faster the film, right, the higher the contrast. So it's going to be a shorter grayscale, right? There's going to be more black and white. The slower the film, the lower the contrast. So it's going to be a longer scale, right? A longer grayscale, more shades of gray. So I thought of a terrible mnemonic to help us remember this with my favorite film now.
Oh my goodness.
50 Shades of Grey was a slow film. That's what the critics are saying, right? If it's showing 50 Shades of Grey, it is a slow film speed, right? 50 Shades of Grey was a slow film. This is not an endorsement for the film. Little caveat there. Latitude. Ranges of exposure over which the film will produce diagnostically useful densities, right? So let's unpack that and think about what that means. We're talking about, I think one of the helpful things that we saw the other day was that picture of how wide the latitude is for digital imaging compared to film. Film's automatically going to be a narrower latitude than digital, right? And this is saying it's going to be determined by that inherent contrast. What does that mean? Again, it goes back to the size of those crystals in the film, right? Inside the film emulsion. What is the inherent contrast that the film crystals can provide, right? What is their sensitivity level? So the lower the inherent contrast, the wider the latitude of the film, right? That's going to be a slow film, and we'll see what that means graphically in a little bit. The higher the inherent contrast, the narrower the latitude of the film. So it's going to be a faster film, but you have to be right on the right technique, right? Because if you deviate too much from that technique, it's going to burn the film out. So again, another mnemonic with 50 Shades of Grey. 50 Shades of Grey is not narrow-minded, right? Just if we're talking about a wide exposure latitude, right? It is broad-minded, if you will. It is also going to have a wide number of grays in it, okay? The image is going to allow for more shades of gray. Okay, here's what that looks like graphically, right? This comes out of Bouchon. And we have latitude A and latitude B, right? Which one of these looks like it is going to be the narrower latitude? A. Exactly right. And we can see that right here. So here's a little narrow window. We have this gray box is representing a usable optical density, right? So we have what's called a toe to the curve down here at the bottom and a shoulder, right? That means that these films are made to where they have to get some kind of exposure before they start to do anything. Prior to that, it's just going to be noise, right? It's just going to be background. Once it reaches that threshold of exposure, and it's going to be a pretty small threshold, right? This is a millirankin. It's going to start to display optical density. All those little silver halide crystals are going to start firing off, right? And then we're going to get to a point where all of a sudden we've just burned it out. That's what that shoulder means. right? We've gone beyond the usable optical density. We could continue to X-ray this film all day long. It's not going to do anything else, right? So in terms of a latitude, exposure latitude, we see that this one is going to move more slowly. It's a slower speed film, right? But because it's slower, it's going to have a wider exposure latitude, right? So 50 Shades of Grey was a slow film, right? It had a lot more contrast in it, and it's going to require a wide way of thinking about things, right? So it has a wide exposure latitude. Okay. Anything that I can do to make this junk memorable, because otherwise it's just pixels on a white screen. Okay. All right. Thank you. This is a crazy picture. I want to talk to you a little bit about this picture. This is from Time Life magazine, 1950 something. These women won a proper spine contest. It was created by some kind of chiropractic organization. They X-rayed these ladies' spines to determine who had the best posture, I think. Remember when posture was important? I don't. But apparently they had really good posture. All right, that is that.